All right, guys, in this lesson we're going to be looking at sample sizes and margin of error. So our objective here is just to determine the sample size necessary for a confidence interval for population mean and a specified margin of error. So essentially we've been working forwards this whole time to try and figure out the population mean and standard deviation to give an estimate of that. Now we're going to kind of work backwards to see what would be an appropriate sample size if we're given some of that information to start with. So we know that margin of error is essentially what size sample is necessary for a confidence interval with a specified margin of error. And so how we would do that is we would use this formula, because this is the formula that we have been using, or that we did use in the last lesson, essentially, or at least this part of the formula, in order to figure out our standard deviation, or our mean, basically. However, there's some issues with this formula. First, we do not know the standard deviation of the sample size because we haven't collected the data yet, which would be fine because we could use our standard error, which doesn't necessarily represent our standard deviation. But we don't even know the standard deviation of the sample size, so we can't even use our sample error. However, we also can't calculate the critical value, this t right here, without knowing how many sample individuals we need. If you'll remember that in order to calculate t, we needed the variable degrees of freedom. And the degrees of freedom is essentially just the number in our sample minus 1. That's one little element that we needed to figure out t. Well, if we are trying to find how many is actually in our sample, or what the smallest number we need in our sample is, then we can't find t. So essentially, we have to use another formula, basically. And so we have to use a previous sample of standard deviation to estimate our standard error right here, and we use a standard normal value of z to estimate t. So we have to use our z-score instead of t, or z-table instead of our t-table, in order to estimate this critical value right here. So we're using this formula instead to answer these questions right here for margin of error. So here's a couple examples. The first one is researchers would like to estimate the mean cholesterol level of mu of a particular variety of monkey that is often used in a laboratory experiment. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. The previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. So again, we're using this formula right here to solve. We know that they give us a standard deviation of 5 right here in our problem. That's what they give us right there. We also know that we need to find our critical value at a 95% confidence level. And if you'll remember, if we're given this graph right here, we know that our 95% confidence level represents this area right here, the area in between the lines. That's our 95% confidence level. However, we don't know the area on either one of the tails. Well, either one of the tails combined represents 5%, or our other 5% of our total area. But when we're plugging this into the calculator, we only want 1/2 of that 5%, or 1/2 of that tail, basically. And so half of 5 gives us 2.5%. So really, we're actually finding the area of 97.5% instead of 95%, because 95 plus 2.5 gives us 97.5. So remember, if we're wanting to find our critical value using z, we go to second vars, and we find the inverse norm in order to find that z value. And then under our area, we would put 0.975, because that's going to be our area that we're trying to find. Our mean would be 0, our standard deviation would be 1, and then from there that gives us a critical value of 1.96 right there. So that's how we would solve that problem right there. Just make sure that you're plugging in the right value for that inverse norm function. From there, we literally just solve. So we know that 1.96 is going to represent the z, 5 is going to represent our standard deviation, and then we know that our margin of error just needs to be 1. So we're plugging in 1 for our margin of error is less than or equal to 1.96 times 5 divided by the square root of n, and we're solving for n. And when we do all that math, what we come out with is n is greater than 5 divided by 1 divided by 1.96 squared, which gives us a total of 96.04. So n has to be greater than 96.04, which means that we have to have a total of 97 monkeys, in our sample in order to achieve our 95% confidence level and have a margin of error of 1, basically. So that's how we would solve that problem. Let's look at another example. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate mu at the 90% confidence level with a margin of error of at most 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to meet the administrator's goal? Show your work. So, again, they give us a margin of error of 30 right there. They give us a standard deviation of 154 right there, and a critical value of, again, it would have to be our inverse norm function. So, inverse norm. They give us a 90% confidence level, so I know that the two tails are going to represent 10%. I only need one of the tails, so it's going to be a 95% area for that inverse norm function with a mean of 0, standard deviation of 1, and then that gives me my z value of 1.65. From there, I plug that into the equation where 30 is greater than 1.65 times 154 over the square root of n. I solve for n. N is now greater than 154 divided by 30 divided by 1.65 squared, which gives me a total of 71.7. So I need to have at least 72 students in the sample in order to achieve my 90% confidence level with a margin of error of at most 30 minutes.